In the last video, we connected up complex numbers with polar coordinates, a Calculus 2 topic. In this video, we're going to connect up complex numbers with another Calculus 2 topic, Maclaurin series, through what's called Euler's formula. By the way, this was on Friday's worksheet, so you may have already done this, but I know that not everybody got through Friday's worksheet, but this is really, really, really important for you to see, so I'm making this its own separate video. Okay, this is going to be a kind of follow or nose thing. I'm going to start off with something you might not see while I'm doing it. I promise the punchline at the very end is very cool, very impressive. So the thing that we want to start off with is think about the exponential function e to the x. And so we should know off the top of our heads, like the Maclaurin, Maclaurin series for this. This is a very good thing to know. 1 plus x squared plus x squared over 2 plus x cubed over 6 plus ... And so what I want to do is that I want to write down the Maclaurin series for e to the I theta. So what this is everywhere we see an x, we're just going to replace it with I theta. And to do this, we're going to have I theta raised to the various powers, I theta raised to the nth power. And I theta raised to the nth power is, of course, I to the n times theta to the n. And so from previous sets of videos, we've emphasized the fact that I raised to different powers. There's a nice pattern to that. It loops around with a period of 4. So in particular, I to the first is 1. I squared is, I to the first is I squared is -1. I cubed is -I to the fourth is 1. We did this in a previous video. Check for yourself if this doesn't feel familiar. Check this all out for yourself. And then it repeats. I to the fifth is I to the sixth is also -1. I to the seventh is -I to the eighth is 1. And so this I minus 1 minus I1 repeats I minus 1 minus I1. If we were to do I to the 9th, 10th, 11th, and 12th powers, again, we would have I minus 1 minus I and 1. So at this point, let's very carefully write out e to the x. I'm going to write out the degree 8 Maclaurin polynomial for e to the x, 1 plus x squared over 2 plus x cubed over 6. Maybe I should use factorials here, 3 factorial, plus x to the 4th over 4 factorial, plus x to the 5th over 5 factorial, plus x to the 6th over 6 factorial, plus x to the 7th over 7 factorial, plus x to the 8th over 8 factorial, plus ... and we cut it off right here, degree 8 Maclaurin polynomial for e to the x. So now e to the I theta is going to be, everywhere we see an x, we replace it with I theta plus I theta squared. Let me just write all the I thetas real quick. I sometimes get a bit carried away with the color coding here. Well, I entertain myself with the Zoom whiteboard sometimes. Okay, so now we're getting all of this filled in here. This is just filling in. So this is what e to the I theta, the Maclaurin polynomial for e to the I theta. Oops. That was supposed to be a 7 factorial there. And there's our 8 factorial. Okay, so what happens? Let's rewrite this. And I want to do the following. I want to replace, stuff like I theta cubed is going to be I cubed theta cubed. I theta to the fourth will be I to the fourth theta to the fourth. And I want to use this dictionary right here to do replacements. And then the other thing that I'll observe, that some of these terms will have i's in them. Some of these terms will not have i's in them. I to the 6 does not have an I in it. I'm going to kind of write this out separately. I'm going to write out the terms with i's in them separately than the terms without i's. So 1. And then the next one plus I theta. So I'm going to write that separately down here. I squared will be -1. So this will be -1 times theta squared all over 2 factorial. This will be I cubed theta cubed. I cubed is -I. So I'll put that on the lower level here. -I theta cubed all over 3 factorial. And going back and forth, I to the 4th theta to the 4th. I to the 4th is 1. So plus theta to the 4th over 4 factorial. Then, 1 second. I to the 5th is just I. So we're back down here. I to the 6th will be -1. I to the 7th will be -I. And I to the 8th will be +1. And of course, there will be, more terms coming. And so let me do one more thing here. Downstairs, all of these, why did I separate out all of these? Because they all had i's in them. So what I'm going to do is that I'm going to get rid of all of the i's. I'm going to get rid of all of the i's. I'm going to factor out an I from all of this stuff. So this is going to be I times theta minus theta cubed over 3 factorial plus theta fifth over 5 factorial, minus theta to the 7th over 7 factorial. Okay, I'm going to pause here for 15 seconds for you to look at this and see if you notice anything. Okay, don't know how close that was to 15 seconds, but does this look familiar? Maybe this is a little bit, I'm using theta here instead of x, but 1 minus theta squared over 2 factorial plus theta 4 over 4 factorial minus theta 6 over 6 factorial. That should look familiar. Replace with x, 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. This is exactly going to be, stopping here, this is the degree 8 Maclaurin polynomial for cosine of theta. And we keep going, we get the Maclaurin series for cosine of theta. And so then what is this down here? Theta minus theta cubed over 3 factorial plus theta fifth over 5 factorial, ... This is going to be in the Maclaurin series for sine of theta. And so what is our big punchline here? E to the I theta is cosine theta plus I sine theta. This is important enough I need to write this again. E to the I theta is equal to cosine theta plus I sine theta. And so what this says is that, if you're raising something to this imaginary power, e to the I theta, you can break this down as a real number. Cosine theta will be a real number plus I times another real number. We're writing this as a complex number as the sum of its real and imaginary parts. This is very cool, and we will use this a lot in the future. So then it's worth to kind of finish off these videos here. A couple also really cool things. Well, what are some fun values to plug in for theta here? And maybe the first one to plug in is theta is equal to 2 pi. So e to the 2 pi I is equal to cosine of 2 pi plus I times sine of 2 pi. The sine of 2 pi is 0. Cosine of 2 pi is 1. So e to the 2 pi I is just 1, which is a pretty cool formula. And then to finish off this video, e to the I pi, this might end up producing something you've seen before, but you might not know where the formula comes from. And so this is the big finale here. E to the I pi, we plug in theta is pi. Cosine theta becomes cosine of pi plus I times sine of pi. Sine of pi is still 0. Cosine pi is -1. And so if you've ever seen the equation e to the I pi is equal to -1, this is where it comes from. This is where it comes from. And to write one last thing, e to the I pi is equal to -1. I can move the -1 to the other side and write e to the I pi. Let me make this nice and big. E to the I pi plus 1 is equal to 0. And some people would say this is one of the most beautiful equations in mathematics because of it just ties, it's a very simple statement. There's only 1, 2, 3, 4, 5, 6, 7 symbols here, but it ties together so many different things in math exactly once. So like the most important numbers in math, I think, 0 and 1, we would say. Also, e to and pi are also going to be very important numbers, along with I, and all of those numbers are appearing exactly once. What are the most important operations in math? Addition, multiplication, I times pi, exponentiation, e to the I pi, along with equality. And we have all of these different things occur exactly once in this formula, which is very cool. Okay, so I hope you enjoy this video. We'll do more applications of this in our next video.